Hello, this is the next session in the course on nanoelectronic device fabrication and characterization. What we did last time was to learn about carbon nanotubes and the CVD process. What we will do today is to continue a bit more about the CVD process, and then we come to atomic layer deposition or ALD, and then look at examples of nanostructures that are obtained from ALD. Now, at the end of the class last time, I pointed out that there is a mundane application of the chemical vapor deposition process in making cutting tool bits, that is coating on cutting tool bits for the machine shop. What they look like are this is a typical cutting tool bit for cutting, for example, high speed steel, and what it consists of at the last layer is a coating of tin nitride, which gives its golden glow. Beneath that is a layer of aluminum oxide measuring about 5 micrometers. Beneath that is a titanium carbonitride coating, all of this sitting on top of several millimeters of a tungsten carbide cobalt substrate, which really is the total cutting tool. This aluminum oxide layer at the top actually enhances the lifetime of this cutting tool by a factor of as much as 10. Now, the reason it happens is because of the teeth that you can see here. These are aluminum oxide crystals that are essentially vertical or perpendicular to the substrate, thin long needles in the alpha Al2O3 phase of aluminum oxide. On the right side is the kappa alumina phase, which can also be obtained, all of these by a CVD process that uses aluminum trichloride as the precursor along with carbon dioxide and hydrogen, and the temperature at which this works is about 1000 degrees and more, and the result is obtaining Al2O3 coatings on the substrates. Now, what I want you to look at is that these are very thin long needles of Al2O3, crystals of Al2O3, which have the cutting force necessary for cutting high speed steel, and these are very thin in terms of nanometers, although they are long, several micrometers long. On the other hand, the kappa alumina phase, which can also be obtained by the same process under slightly different conditions, is also a hard material for cutting metals, and that consists of essentially nanometric grains of kappa alumina, which is an orthorhombic phase of aluminum oxide. I want to point out that this is a very effective cutting material, kappa alumina, and the nanometric nature of it gives it additional mechanical advantage. Now, we come to look at a phase diagram of carbon, which is the equilibrium phase diagram of carbon, where pressure is plotted on the y axis and temperature on the x axis, and different forms of carbon, allotropes of carbon, are plotted on this graph. Now, what I want you to see is that diamond is a high pressure, high temperature phase of carbon, that is, under equilibrium you need high pressure and high temperature to obtain diamond, otherwise it is mostly graphite. But at this lower end corner over here is a region where the CVD process is capable of producing diamond. Instead of at high pressure and high temperature, these are at a much lower temperature and much lower pressure. So, CVD has the capability to produce metastable diamond under these conditions, and it is actually a process that is used today in producing films of diamond for various purposes, including abrading. Now, this is the kind of a chamber, CVD process chamber, in which such depositions can be done. Actually, carbon allotropes can be synthesized by thermal CVD, different carbon allotropes, by which I mean diamond, graphene and carbon nanotubes. So, these are different allotropes, and all of that requires a hydrocarbon and excess of hydrogen in the chamber, and typically a catalyst, especially for carbon nanotubes and graphene. It requires a catalyst, and the deposition temperatures typically range from 700 to 900 degrees or slightly above. So, the same thermal CVD process is capable of giving us different allotropes of carbon. Now, let us look at that a little bit more. It involves the use of hydrocarbons, saturated and unsaturated, like methane, acetylene, ethyl alcohol and so on, and nanometric diamond, that is, diamond films which have grains of diamond in the nanometric range, can be produced at low pressure and high temperature in great excess of hydrogen by the CVD process. Now, carbon nanotubes call for low pressure and moderate temperatures and the presence of a catalyst, especially a transition metal like iron, nanometer crystals of iron as the catalyst. Graphene, which is a more recently discovered allotrope of carbon, which is a single layer of graphite carbon atoms, requires low pressure, moderately high temperatures and especially on copper substrates. For example, with copper acting as a catalyst, exactly one layer of graphene can be deposited on copper by the CVD process, and further reaction is inhibited because copper is then completely covered by a monolayer of graphene. Therefore, using a copper substrate and the CVD process is very efficient in giving us a monolayer of graphene, on which a lot of work has been done recently. Now, graphene, what we are looking at is a photograph of a graphene layer produced by CVD in transmitted light. In the middle, you are seeing a monolayer of graphene, and you are able to see that because graphene monolayer of graphene absorbs 2.3% of white light, and therefore, one is able to see graphene, and then next to that is a bilayer of graphene, 2 layers of graphite on top of each other. So, that is a bilayer of graphene. So, these are produced rather readily now by the CVD process. Now, CVD, it turns out, is also an ideal process for layered or 2-dimensional transition metal dichalconides like MOS2. All of these have become a rage in the research field today following the discovery of graphene, which is a monolayer of carbon. Similarly, MOS2, one can get a monolayer of MOS2, which is a transition metal disulfide. Now, these can be obtained by the CVD process, for example, using molybdenum hexacarbonyl as one precursor along with hydrogen sulfide, and under the ideal right conditions of CVD of high temperature and high pressure, low pressure, one gets molybdenum disulfide as the product, and what you see in these SEM micrographs are monolayer pieces of very well shaped triangular shaped MOS2 layers, and what you see below are Raman spectra of these monolayers, which can be interpreted to tell us whether it is a single layer, double layer and so on, and these happen to be single monolayer molybdenum disulfide layers. Now, we now move from CVD, of which we have learned some capabilities, from CVD to atomic layer deposition or ALD. And before you go, we recognize that CVD is a steady state process. It involves continuous flow of reactants, and therefore, there is the possibility of side reactions or undesired reactions or gas phase reactions, which can produce byproducts which can contaminate the film that one is interested in obtaining. That is because more than one reactant is present in the chamber at any instant. Atomic layer deposition is designed to overcome this particular drawback. Atomic layer deposition is already a well developed technology with applications in semiconductors, nanoelectronics, in particular in the deposition of gate dielectrics in the more recent versions of CMOS technology. Intel processors starting with the 45 nanometer generation and later include a thin layer of hafnium oxide, so called high K dielectric or a dielectric with a large dielectric constant, that is deposited by atomic layer deposition. There are various reasons that ALD has become a method of choice for this purpose, because unlike ALD, conventional evaporation and sputtering give rise to porosity, which is undesirable in very thin dielectric layers, and therefore, non-porous layers are required. In addition, ALD produces layers of extremely uniform and reproducible thickness, low stress and low defect density, allowing for growth on amorphous substrates also. Furthermore, besides VLSI production, ALD has proven essential to the deposition of gate dielectrics on device substrates without native oxides such as germanium, gallium arsenide and gallium nitride. What is shown here in the micrograph is a structure that is obtained, that is part of the Intel technology, where the high K dielectric HFO2 of thickness less than 5 nanometers is deposited by ALD, and then the gate electrode is titanium nitride also deposited by ALD. This next micrograph shows the capability of ALD in really producing conformal coverage of very high aspect ratio features that are common in today's VLSI devices. So, what is shown here is a thin layer of tungsten nitride that is covering this deep trench and that is insulating copper, which is the metallizing layer from silicon. Copper diffuses rapidly into silicon, affecting device performance, and therefore, the tungsten nitride is used as a diffusion barrier, very thin diffusion barrier that is now covering this very deep trench in a very conformal fashion. Only ALD can do this. ALD is also used in DRAM manufacturing, for example, by Samsung, and what is shown here is a structure again with a deep trench. So, this is so called DRAM trench, where one has a layer of aluminum oxide that now separates silicon from copper. So, therefore, ALD is capable of covering very fine features conformally, that is those features are present in today's VLSI devices. What is ALD? We have shown examples. What is ALD? ALD may be defined as film deposition technique based on sequential use of self terminating gas solid reactions. So, the operative thing is sequential use of self terminating gas solid reactions. As I said, in CVD there is a continuous flow of all the reactants involved, whereas in ALD by contrast there is a sequential flow of or pulsing of reactants into the deposition chamber. ALD is a chemical process and is a variant of CVD actually, because chemical reactions are involved, and ALD, as I said, is suitable for depositing very thin layers, including a monolayer of inorganic materials such as oxides. ALD is suitable for depositing extremely thin layers over large areas. So, one advantage is that it is capable of producing very thin uniform layers on substrates as large as 300 millimeters, which is today used in VLSI manufacture. In ALD, reactants are injected in alternating pulses into the reaction chamber, and vapors of one reactant at a time are injected in as a pulse and allowed to absorb on the substrate surface. Under optimum conditions, one monolayer of each precursor adsorbs onto the surface, resulting in a self limiting adsorption process. It depends on a self limiting adsorption process. The unadsorbed or excess vapors, because we only require a monolayer, are removed by injecting a pulse of inert gas and by pumping. Now, the basic characteristics of ALD involve steps of self terminating reaction of first reactant A purge or an evacuation to remove unreacted A material and the byproducts, then inject a self terminating reaction of the second reactant B, and then another purge. So, together these 4 steps are considered to form one ALD cycle, and this cycle is repeated depending on the thickness of the material that one requires. It can be illustrated very well by the example of aluminum oxide deposited by Al2O3 using trimethyl aluminum or CH3 thrice Al and water as the 2 precursors. So, what is shown in this cartoon is a substrate such as silicon, on top of which typically there is a hydroxyl group unless the pressure is very low, but CVD and ALD is done not at very low pressures, and therefore, one can expect these OH hydroxyl groups to be present on the silicon surface. So, trimethyl aluminum is shown here in this diagram, and trimethyl aluminum comes in as a vapor, and what happens when that occurs is that a reaction occurs whereby the hydrogen that is over here then gets attached to one of the methyl groups, producing methane, which escapes as vapor, and now you have what you now have is an aluminum oxygen bond and then dangling CH3 groups on this particular molecule. And when the entire substrate is covered, what you now have is a uniform layer of this aluminum oxide precursors over here. This is not aluminum oxide yet, but you have these dangling bonds of trimethyl aluminum. Right now it is dimethyl aluminum, and methane escapes, and therefore, what you now have is a uniform layer of this particular structure. Now, at this stage water is introduced as water vapor. So, this is HOH that comes in, and when that happens, then what happens is that this hydrogen now attaches itself to oxygen over here, and there is oxygen that is that bridges to aluminum atoms, and therefore, what you now have is oxygen bridges and hydroxyl surface groups that are formed now, and when this particular step is complete, what you now have is a uniform layer that has hydroxyl groups and then oxygen aluminum oxygen bridges. So, if this process is continued, therefore, one builds up these aluminum oxide layers. So, each cycle is under ideal conditions capable of giving us one such layer, and if this is repeated, cycle is repeated, one has this uniform layer, uniform aluminum oxide film of the desired thickness, that is a function of the number of cycles, ALD cycles. Now, that is a very good example of the ALD process, but aluminum oxide has very good precursors, namely trimethyl aluminum, which is very suitable for the ALD process. If you want to do zirconium oxide, for example, which is a zirconium oxide is a high K dielectric. If you want to do zirconium oxide, for example, you do not really have such a conveniently structured molecule. What you have is zirconium acetyl acetonate, of which the structure is shown here. Now, this is much less suitable for the ALD process, as we shall see later. Now, what are the process parameters for ALD? It is the precursor pulse duration, substrate deposition temperature, substrate temperature, purge duration, pressure, all these together form different parameters that control the ALD process. The chemical nature of the precursors themselves, of course, is fundamental. Now, what is shown here is a schematic of the what we are going to see next is an ALD cycle. A typical cycle lasts only a few seconds, a total cycle, and that is illustrated in this particular animation, as you will see. Okay. So, what you will see is the completion of 4 parts of the cycle, and one cycle therefore is repeated to get the desired thickness of whatever film we are interested in. So, thickness is proportional to the total number of ALD cycles. So, that is the primary metric we have for measuring the thickness or controlling the process. Now, what are the requirements or characteristics of the ALD process? The substrate surface must be in a controlled state, for example, at a constant elevated temperature. The parameters to be adjusted are the reactants, the chemical nature of the reactants or the precursors, the substrate itself, the nature of the substrate, substrate temperature, precursor pulse duration and purge pulse duration. All these are variables that are specific to a particular process. That is, the right choice of these parameters has to be done for the deposition of a particular particular material by ALD. Now, what ALD involves is the chemical adsorption or the adsorption of the precursors on the surface. Actually, both physical and chemical adsorption are involved in the ALD process, in a typical ALD process. So, what you have is precursors coming and landing on the substrate and adsorbing on the substrate. Now, there are different kinds of adsorption mechanisms or chemical processes that involved. When the next precursor comes in, that is, you have one layer and the next precursor comes in, what can happen is ligand exchange. So, a part of the molecule that comes in then exchanges a part of the molecule that is already absorbed, and that is called ligand exchange, and therefore, what you are left now is with this kind of a layer, as in the case of aluminum oxide. Or you can have dissociation. So, the incoming molecule or incoming precursor molecule dissociates, and therefore, you have a different kind of a chemical circumstance on the substrate. Or it can be association, the incoming molecule then gets associated with what is already on the substrate and you have an association. So, these are different cases. Now, what we saw in the case of aluminum oxide represents ligand exchange, that is we now have CH3 thrice Al and then HOH or water molecule, and what we now instead get is out of that a methane molecule and then the dangling bonds of trimethyl aluminum on the surface. So, this is a case of ligand exchange, and it turns out that ligand exchange of this sort is more suitable to obtain uniform layers with ALD process. Now, as I said, ALD involves a self terminating surface reaction of an adsorption process. Now, it is possible to consider different kinds of self terminating reactions. What I have shown here are the amount of adsorbed material as a function of time in 5 different types of adsorption. So, what we now have here is a quick saturation and a complete saturation. Now, in the second one in B, what you have is saturation, but then again desorption and so on. So, there are different kinds of reactions that can happen on the surface in the ALD process. What is desirable is in ALD, chemisorption by ligand exchange is preferred because it provides us with this rapid saturation and stable saturation as in the figure A over here. Now, as I said, in ALD ligand exchange is preferred, and saturation through ligand exchange as in the case of aluminum oxide is controlled by 2 factors, namely steric hindrance and by the number of reactive sites present on the substrate. Now, what is steric hindrance? Now, to have an idea of what is steric hindrance, we go over here and look at what zirconium oxide, zirconium acetyl acetonate looks like. What you have here is a large molecule. The central part represents the precursor, namely precursor to ZrO2, which is what is desired, but there are many methyl groups that surround the central part of the molecule, and these have to be removed. But when this molecule adsorbs on the surface, then these methyl groups which have to be removed cover a lot of area. So, when they are gone, what you are left with is a much smaller area that is covered by the desired zirconium oxide species, and therefore, when the next molecule comes here, there is a significant amount of void between this ZrO2 entity and the neighboring ZrO2 entity after the reaction takes place. Therefore, the coverage is much less than 1 monolayer after 1 cycle, and therefore, this is called steric hindrance of the process. Now, coming back to the steric hindrance case. So, you can have ligand exchange controlled by 2 factors, namely steric hindrance and the number of reactive sites as shown in this cartoon. Now, one parameter that is important is growth per cycle, that is the unit that is used in ALD to describe different ALD processes. What is the amount of growth that takes place per ALD cycle? Now, the ideal of course would be to grow 1 monolayer per cycle, but this does not usually occur due to steric hindrance as I pointed out. Now, there are 3 models to describe the effect of steric hindrance on growth per cycle. So, what I have shown here are 3 different kinds of situations that can arise when we use different kinds of precursors. Now, what is shown at the top or model 1 shows a ligand that is rather large in size, physical size, and therefore, when reactions occur, there is a significant amount of void that is left on the substrate. The model 2 is chemisorbed large molecule over here, and when that happens, as the adjoining figure shows, there is a significant amount of void, much more than in the case of model 1, a significant amount of void on the substrate as in the case of the zirconium acetyl acetonate that I mentioned a while ago. So, this cannot lead to a complete coverage in 1 cycle. Now, model 3 is the one where the size of the ligand molecule here is small, and therefore, you now have a coverage of the substrate that has much less void than in model 1. Therefore, what is ideal for atomic layer deposition is model 3, where you can approach a significantly greater degree of coverage of the substrate per cycle. Now, let us look at the numbers. Now, as I said, the case of Al2O3 using trimethyl aluminum and water is represents this kind of a situation, is represented by this kind of a situation where you now have a significant amount of coverage per cycle. Now, the zirconium acetyl acetonate, as I already told you, represents this kind of a case where there is a large amount of void, and therefore, the percentage coverage of the substrate per cycle is bound to be less than in the case of model 3. Now, in model 1, which is where I have shown these large ligand molecules, just a few processes can be assumed as model 1. There are not many examples of that, and when that is used, 25% of a monolayer is formed per cycle. Only about a quarter of the substrate surface is covered per cycle. The case of zirconium oxide, for example, would be such a case when zirconium acetyl acetonate is used as the precursor. Model 2, which is where we have these chemisorbed ligands over here, is often used to model the ALD process, and the percentage coverage is less than 20% of a monolayer in such a case, large ligand, large void space. Model 3, which is where we have shown these small ligand molecules covering the substrate pretty at a low porosity, then is applicable to some ideal ALD processes such as trimethyl aluminum and water, and this is the most optimistic one, whereby the growth per cycle is about 30% of a monolayer, approximately 1/3 of a monolayer. Now, how about the growth per cycle and its dependence on temperature? How does the temperature of the substrate play a role in all these things? Now, we have 4 different kinds of variation. One is where the growth per cycle reduces as the temperature is increased. In case B, the growth per cycle is independent of temperature, and we can really see that such a process where temperature is not a factor would be really desirable in a practical process. Growth per cycle would increase with temperature, and growth per cycle in D behaves in an odd way, increases and then decreases as a function of temperature. Now, investigations show that the reaction of trimethyl aluminum with water to give Al2O3 on silicon oxide surfaces is rather insensitive to temperature. That is, it behaves more like B over here, where the growth per cycle is independent of the substrate temperature. But this is not completely true, because the temperature affects the adsorption of the substrate surface, and therefore, the pulse duration per precursor should be adjusted so that self terminating adsorption reaction takes place. So, nevertheless, aluminum oxide using trimethyl aluminum and water represents a very good process that describes a temperature independent growth per cycle. Now, there is something known as the ALD window, atomic layer deposition window, that is shown over here. What is shown here over here is the growth rate, that is the growth per cycle as a function of temperature. What you can see is that there are several regimes where growth is increasing with temperature or decreasing with temperature or constant with temperature. Now, what is shown here in the center is the region what is known as the ALD window, where the temperature is the growth rate is independent of temperature. What happens at low temperature and what happens at high temperature? At low temperature, for example, in this lower branch, the reaction is not completed in the given pulse time. Therefore, as the temperature increases, the reaction rate increases and the growth per cycle increases. Now, on the upper part of this particular branch, what we now have is the reduction in the growth per cycle as a function of increasing temperature. Now, what happens is that in this case adsorption and condensation of the precursor takes place without any reaction occurring, and therefore, actually the growth rate goes down. Now, at the high temperature end, in this branch of the cycle or in this branch of the curve, as the temperature increases, desorption takes place, rather desorption takes place over here, and therefore, growth goes down. Now, over here in this part of the particular diagram, if the precursor decomposes as a function of temperature, then what you really have is not an ALD process, but a CVD process, but growth rate goes up. So, what one wants to have is this kind of a region, the ALD window, where the growth rate per cycle or growth per cycle is independent of temperature, and for every pair of ALD reactants, one has to examine and identify the ALD window where the growth is independent of temperature, because to have a controlled process and therefore, the number of layers to have that is therefore, to determine the number of layers one wants to have to get a given film thickness, it is ideal to operate in this ALD window region where the growth rate per cycle is independent of temperature. Now, what about the precursors? What are the requirements of chemical precursors? After all, this ALD is a chemical process. So, what are the requirements of the ALD process? Now, one can think of describing the two precursors by different terminologies. Ligand precursor. Ligand precursor is used to prepare the surface of the next layer, and it defines the kind of material for growth. For example, water for oxides, nitrogen for nitrides, and so on. Remember, we came across aluminum oxide, we also came across titanium nitride in that Intel device, and therefore, nitrides are also materials that can be deposited by ALD. So, nitrogen would then be the ligand precursor for forming nitrides, just as water is for oxides. The so called main precursor is the metal containing precursor. For example, trimethyl aluminum that we came across, and generally one wants to choose a reactive, considerably reactive and significantly volatile compound of a given metal as the ALD precursor, that is also stable, that is it does not decompose at the temperature of the substrate. Therefore, it is important to identify the main precursor that is required for main or the metal precursor that is required for a given process. So, these precursors have to fulfill the requirement for a self terminating reaction, such as trimethyl aluminum for Al2O3 etc., as we have seen earlier. So, these are pretty stringent requirements for identifying ALD reactants for a particular material. Fortunately, there is generally speaking a considerable choice of these materials for main precursor. For example, if one wants to do titanium dioxide layers by ALD, then a compound known as titanium isopropoxide is suitable for this purpose, and it can be used successfully as the metal containing main precursor for TiO2 deposition. So, ligand precursors, as I already said, H2O for oxides, it can be oxygen also. Sometimes it is advantageous to have ozone, because that gives oxygen radicals which can really speed up reactions. It can also be an alcohol through which one can obtain the hydroxyl group, OH group over here. For nitrides, the ligand precursor would be ammonia. and nitrogen. And as I said already, for the growth of pure materials, that is for the deposition of materials that are contamination free, then the ligand precursor should be selected that is appropriate for the main precursor. So, in other words, the choice of precursors is very, very important. What is shown here is a schematic of the ALD reactor that was built in our, that has been built in our laboratory here at the Indian Institute of Science, and it is a so called 5 channel reactor, that it is possible, ideally speaking, using this to build a multi-layer structure by atomic layer deposition of 5 different components. For example, 5 different oxides, one might call them laminates of metal oxides. So, this has the capacity for doing that. Now, what this one shows is the photograph of this system, that of which the schematic is shown here. What you see a lot of over here, this is a close up, what you see a lot of are pneumatic valves, because a significant part of ALD technology involves fast closing and fast opening pneumatic valves, so that precursors can be pulsed into the reactor very quickly, so that the total duration of the cycle itself is just a couple of seconds or 3 seconds or 5 seconds. So, it is very important to have these high speed valves. What is shown here is the photograph of a system that can do both ALD and CVD. So, this is the deposition chamber, and all of this is valving, as I said, high speed valve mechanisms for making for switching rapidly between precursors, and these are sources where, or these are chambers in which precursors are kept at constant temperature, so that the dosage in each pulse is exactly the same. So, what are the features of ALD? To summarize, now, due to self limiting growth mechanism, ALD has these following features: digital control over thickness, which is proportional to the number of ALD cycles, as we already mentioned. It is also, unlike CVD, independent of the flow pattern of precursors. One of the big problems with CVD, or at least an important issue in CVD, is the design of the CVD reactor, so that the flow is proper in order to obtain uniform layers of uniform thickness. But in ALD, since we are pulsing the precursor, there is no flow, and therefore, all we need to do is to ensure enough of reactant supply through pulsing. Conformality and trench fill capability, I have shown already through SEMs earlier of the conformal coverage that ALD is capable of giving, and the trench fill capacity that it has got. Excellent large area uniform deposition. Today, VLSI circuits are prepared on 300 millimeter substrates, and ALD is very suitable for getting extremely uniform layers of oxide materials and nitride materials on such substrates. Reproducibility and relatively straightforward scale up, that is, one can easily scale up from a small substrate to a large substrate, as it has already been done in the VLSI business. Now, because of independent supply of precursors, since the precursors are separated in time and space, that is, 2 precursors are not in the same chamber in the same time, gas phase reactions are reduced or actually eliminated. So, ALD therefore provides layer by layer growth, either a full monolayer or a fraction of a monolayer, generally a fraction of a monolayer at a time, and material composition may be controlled down to the nanometer level, and in ideal cases even to the atomic level, that is, one single layer it is possible to obtain of a given material using the ALD process. So, this offers a simple way to create superlattice and other multilayer structures, or so called nanostructures and nanolaminates. Let us look at some of the examples of nanostructures and nanomaterials from CVD and ALD. CVD first. What are shown here are micrographs, scanning electron micrographs of a CVD process that uses iron acetyl acetonate to produce slightly different materials using pressure as the control. What you have in the left over here, top left over here, is a process that is conducted at 5 torr, relatively low pressure, and what we get here, it turns out by analysis, is iron oxide Fe3O4. When the pressure is raised to 10 torr, the growth of carbon nanotubes begins simultaneously. That is, one gets a simultaneous deposition of iron oxide and carbon nanotubes over here. And when the pressure is increased further to 30 torr, then there is a very intimate intergrowth of iron oxide and carbon nanotubes, which turn out to be multi-walled carbon nanotubes. So, this is an example of growing a composite material that contains carbon nanotubes using the CVD process. Now, these are transmission electron micrographs of such a film over here as in the bottom. So, what you see is complete intergrowth of iron oxide and carbon nanotubes, as you can see here over here. Okay. So, it turns out also that iron particles are embedded within the carbon nanotubes, which actually catalyze the growth of carbon nanotubes in this particular process. Now, what I wanted to say is that point out here is that what we are using as the precursor here is iron acetyl acetonate, which is similar in structure to zirconium acetyl acetonate, which we saw earlier, with iron oxygen bonds and then methyl groups on the outer periphery of the molecule. Now, although carbon nanotubes have been obtained by CVD from various hydrocarbons and alcohols and all that, as I said, this turns out to be the first case where carbon nanotubes are obtained from a metal complex where there is a metal oxygen bond. So, this is possible by CVD. What is shown here is the SEM micrograph, high resolution SEM micrograph of a composite of manganese oxide and carbon grown from manganese acetyl acetonate. Again, this compound has manganese oxygen bonds and methyl groups on the periphery of the molecule. So, this is a growth on stainless steel. The growth temperature is about 500 degrees, rather 700 degrees. What you can see is a very porous structure where the particle size is of the order of a few nanometers. Tremendous surface area, as you can see from here. So, it turns out that this material is very good as an electrode for capacitors, so called supercapacitors. Now, we come to atomic layer deposition using structures that are produced by using anodized alumina to obtain porous alumina, porous aluminum oxide. So, it turns out that by suitable anodization of an aluminum plate, it is possible to grow layers of aluminum oxide, amorphous aluminum oxide, with this kind of an ordered porous structure. As you can see here, these pores are nanometric in diameter and a few micrometers or a few hundred nanometers in depth. So, what you can see here is the uniformity, transmission electron micrograph here shows the uniformity of the pores over here on top of this anodized alumina substrate. So, what these provide are really, again as in the case of CMOS circuits earlier, these provide trenches. So, can these trenches be filled by atomic layer deposition? Of course, the answer is yes, because the aspect ratio here is not very high. What I forgot to mention earlier when I showed the trench structure in a CMOS device, for example, in the DRAM structure, ratio, that is the ratio of the depth of the trench to the diameter of the trench, can be as high as 60. Here is not so high. So, it turns out that using the CVD process, rather the ALD process, it is possible to deposit nickel in these pores of alumina. So, that after the alumina is etched away, when the alumina is etched away after the deposition of nickel, then what you get are these nanotubes of nickel, as you can see here. So, ALD is capable of very nice conformal coverage, filling of the pores, and out of that a very ordered structure of nickel nanotubes. Nickel being a ferromagnet, this can have significant applications. What is shown here is a more complicated structure using porous alumina as before. So, what is done is of course to obtain this kind of a porous structure on top of an alumina plate and then use it as a substrate for film deposition, but in this case it is more complicated. So, what is done is first a layer of TiO2 is deposited. As I mentioned earlier, TiO2 can be done using titanium isopropoxide. So, titanium isopropoxide is done, then a layer of aluminum oxide and then filled with another layer of titanium oxide. So, what you can see here is these 3 rings represent titanium oxide, aluminum oxide and titanium oxide again in these ordered pores. So, you can see that it is actually as good as very high definition lithography. So, ALD is capable of producing very interesting structures of this sort. Nanolaminates, I mentioned earlier that it is possible by ALD to produce multi-layered structures. So, what is shown here is a multi-layered structure of TiO2O5, tantalum oxide and HFO2 in alternating layers. Alternating layers because it turns out that it is possible to control the dielectric properties of such a structure by having these repeated units and controlling the thickness of individual layers. Therefore, it is possible to tailor the dielectric properties and it is possible to obtain nanolaminates with a desired dielectric constant and desired set of dielectric properties. And it also turns out that ALD is capable of producing accurate and abrupt layering, that is a layer of HFO2 and immediately with very little interface a layer of TiO2O5 etc. So, nanolaminates from ALD is possible. Now, another example, so called custom made catalyst. You know, catalysis is a very important part of technology and it is possible, it turns out, using ALD process to design catalysts, nanometric design of catalysts, custom made catalysts. Now, so what one does is to start with an inert substrate, let us think of it as some kind of a sphere, and that is coated with a so called active support. And then the catalyst that we want, such as for example platinum, is coated on this. You can see that this catalyst is now platinum particles are coated by ALD and they cover this substrate over here. And then ALD is used again to stabilize this thin layer of the catalyst. So, you have 4 steps over here and let us look at an example that illustrates what is being done. So, what is shown here on the left in green is a high resolution scanning electron micrograph and by the side of it are transmission electron micrographs of the same thing. So, what we have are cubes of strontium titanate. It is possible to obtain nanometric cubes of strontium titanate. Strontium titanate has a cubic structure and therefore, the morphology of cubes in nanostructures is a natural for strontium titanate, although it is not easy to produce them. And then what is done is using ALD, you can see that there are speckles of platinum on top of these cubes. So, these transmission electron micrographs show clearly that there is this tiny platinum particles and therefore, very large surface area for them given that they are so tiny and excellent as catalysts. So, this TM micrograph here actually high resolution HRTM, so called HRTM, shows fringes which represent that these platinum particles, individual platinum particles are actually single crystalline. So, it is clear from this example that it is possible to use ALD to produce custom made catalysts using nanostructures. Finally, we can go to an example that may be called a play ALD. as opposed to ALD, play ALD. One can play with ALD to produce interesting structures. What you have here is deposition of Al2O3 and inside and around a tobacco mosaic virus, 300 nanometers in length, outer diameter 18 nanometers, inner diameter 4 nanometers. All this grown at less than 80 degrees Celsius by ALD. As I said, trimethyl aluminum is a very reactive precursor, and trimethyl aluminum when used in combination with water, it is possible to, or sometimes with ozone, it is possible to get reactions that produce Al2O3 at temperatures as low as 80 degrees. Such a low temperature is important because we are dealing with a biological material which is unstable at high temperatures, which are typically needed in ALD. Therefore, in this case it is important to conduct the ALD process at a very low temperature. So, what you can see here is the conformal uniform coverage of these tobacco mosaic virus structure without destroying it because a low temperature has been used. So, this particular example illustrates both the capability of ALD to produce conformal coverage of nanometric structures, but also ALD's capability with suitable precursors and suitable process engineering to produce oxide coatings. Aluminum oxide is typically a high temperature oxide, oxide coatings at very low temperatures as low as that compatible with biological materials. Therefore, what we have learned in this particular session is about the ALD process, atomic layer deposition process. What we have learned is that it is dependent on self terminating reactions and sequential such self terminating reactions that are repeated in cycles so as to produce layers of great uniformity in thickness as well as layers that cover large substrates, and also it is possible to produce multi-layer structures and laminates because of the great uniformity that atomic layer deposition provides. So, ALD therefore, because of its capability to produce these uniform structures, because of the capability to produce conformal coverage of very deep trenches in patterns, it has become a staple today of CMOS technology, and it is used in semiconductor technology widely, and it is capable because of its very nature. ALD is capable of producing nanostructures and nanomaterials as illustrated by the nano laminates and as illustrated by the custom made nano catalyst that I just showed you. Thank you.